Hello everyone, welcome to the fifth lecture of 11th week of this course on measurement and instrumentation, and today we are continuing our discussion on data acquisition system, and today we are going to talk about signal generators and will also try to touch upon signal analyzers. Okay. A signal generator is an electronic instrument which produces electrical signals with precise control over waveform shape, frequency, amplitude and modulation. I could have told it's a electronic device, but I am telling that it's a instrument because along with electronic device, it also had different circuit component that we will see in some time. Okay. These signals that are generated by this signal generators served as a control input to testing, calibrating and troubleshooting different electronic and electrical circuits, different sensing and transducing systems, and well calibrated systems also like amplifier and all will require a precise signal from these signal generators. Okay. Although the story of signal generators or history of this is very long, like in early 1920s it was developed, but they were simple sine wave generators. Okay. Initially they could not produce sophisticated waveforms. So very simple and basic waveforms were generated initially with the limited bandwidth and other things. But with technological advancement, they evolved to generate more complex waveform. Like in the previous class itself, we have seen a complex waveform, that is a sawtooth waveform, right? Their accuracy and stability improved significantly over the time, and modern signal generators now offer high flexibility, digital control and advanced features. Okay. This is a typical signal generator. I mean, it can be even more complex, but this is a very simple signal generator. You can see that there are various components of generator, and here is your output. Okay. So you have oscillator. It is connected through different modulations. Okay. There are different modulators. Then you have a voltage controlled oscillator and it is fed to modulator. Okay. And then you have amplifier, attenuators and so on. Okay. But this is not complete signal generator. It can be sometime even more complex for complex waveforms. Okay. So the basic parts of a signal generators are like oscillator, which is the basic building block which can generate the basic waveform, like it can generate simple sine waves. Okay. Then you have different wave shaping circuits which can convert these sine waves into typical shapes like square wave, triangular wave, sawtooth wave and so on. Okay. It also has frequency control unit and amplitude control unit with which you can adjust the output signal frequency and the output voltage levels. Okay. It has different modulators which can provide modulation such as amplitude modulation, frequency modulation as well as phase modulation is also possible. Sometimes amplitude modulation and phase modulation, for that only one modulator is used. It can also produce pulse modulation. Okay. These circuits or these signal generators have sweep generators, which itself is a kind of signal generator which can produce variable frequencies, okay, over certain range. Okay. It has amplifiers to increase signal strength to required level and also has attenuators to reduce output signal to precise low levels. Okay. They have output stage or an output buffer to provide impedance matching with the next stage, and all of these are triggered together. So mostly it also has a synchronization circuit, which is a kind of pulse circuits or pulse generating circuits for timing applications. Okay. The signal generator process starts with the oscillator, which generates a stable and repetitive waveform, for example a sine wave. Okay. So oscillator becomes very crucial part of a signal generator, and it is a fundamental and widely used electronic instrument not only in the generator but in other applications also. Okay. It serves as a convenient source of test signals for various electrical and electronic measurements. Alright. They are commonly used to supply power or test voltage in circuits, particularly when you want oscillating voltages or oscillating currents. Okay. Typically, the oscillators produces a continuous sinusoidal output signal. Okay. It is a fundamental part of any signal source. Alright. And we have seen that it is the first stage of any signal generators. Okay. It can generate signals with known frequency and amplitude. So you can be sure that whatever signals that you are feeding to the next stage, maybe to the frequency modulator or to the amplitude modulator, is fixed in the frequency and amplitude. Okay, and it can operate over a wide frequency range, say from few kilohertz to or few hertz even to certain gigahertz. Okay, a basic oscillator system consists of two main blocks, one oscillator section and another is the attenuator section. Okay, the overall performance of the instrument depends on both the section, the oscillator section as well as the attenuation section. Okay, accuracy, stability and low distortion are mainly determined by the design of the oscillator, while the accuracy of the output amplitude depends on the design and quality of the attenuator. Okay, these oscillators are classified in several ways, but there are two ways of classification, I would say, for the oscillators. First is the frequency range over which they are used, and second way to classify them is on the design principles based on which these oscillators are built upon. Okay, based on the frequency range over which they are used, the oscillators are of different type. Like we have audio frequency oscillator, which can typically generate a wave range of 20 hertz to 20 kilohertz. Okay, RF frequencies oscillators or RF oscillators are like 20 kilohertz to 30 megahertz, but of course this is a wide range, even it can go beyond, but right now we are considering low RF range only. Okay, then we have video frequency oscillators, which can produce anything to 5 megahertz. High frequency oscillators can range from or can generate oscillations from 1.5 megahertz to 30 megahertz, and we have VHF oscillators, very high frequency oscillators, which can generate frequencies of the order of 30 megahertz to 300 megahertz. Okay, now this is based on the frequency range over which they are used or which they can generate. Okay, now according to design principle based classification, oscillators are divided into two main categories. We have feedback oscillators and we have a negative resistance oscillators. Okay, and feedback oscillators uses an active device such as an amplifier whose output is feedback in phase to its input. Means that I am talking about in phase feedback, means that I am talking about a positive feedback. In case of operational amplifier, we have seen feedbacks in more detail. Okay, so the feedback oscillator uses an active device, for example, a op amp itself. Okay, whose output is fed into its input with in phase to the input, or it is a positive feedback which causes basically a regenerative action. Okay, and when you have this kind of feedback, okay, they produces oscillations. Okay, now this is a simple example of this whatever we are discussing right now. Okay, you have this amplifier and you have this feedback network. Okay, and H is, for example, the feedback factor. Okay, if the gain of the amplifier is G, and if G is the gain, means that G is equal to this output E naught by EI. Okay, and if the feedback factor is H, okay, in that case, say gain with feedback, I am calling it GF, is equal to G by 1 minus GH for positive feedback. Okay, where GH is called the loop gain, and if GH is equal to 1, okay, and since GH is a complex term, I am also writing a J0 to show that the complex part is null. Okay, GH is 1. Okay, if GH is 1 in this case, I have G by 1 minus 1, means that GF is equal to infinite. Alright. Now the physical meaning of this is that the signal input voltage EI can be reduced to 0 without affecting the output voltage. Therefore, the amplifier can provide an output without having any input, and such a self-excited source is termed as a feedback oscillator. Okay. Now, feedback oscillators are classified into three categories. We have RC oscillator, or we call it resistance capacitance oscillators. We have LC oscillators, which is inductance capacitance oscillators, and we have crystal oscillators. Okay. RC oscillators may be one of the two following forms, can be in the Weinberg form, we call it Weinberg oscillator, and we also have a phase shift oscillators. Okay. Now, all these oscillators that we are seeing are based on the Barkhausen criteria. Okay, if you are aware of this criteria have two essential conditions required for a positive feedback circuit to sustain continuous oscillation. One is the loop gain magnitude must be unity and the total phase shift around the loop must be 0 or 360. Okay. In fact, if you remember, the loop gain magnitude should be greater than 1 to start the oscillation, and after that it will sustain at when it is equal to 1. All right. I mean, this is applied to all kind of oscillator that we are seeing, particularly the feedback oscillators. Okay. Now, LC oscillators uses a tank circuit which is basically based on inductance and capacitances to generate high frequency sinusoidal signals. Usually the RC oscillators are used at lower frequencies and LC oscillators are applicable for higher frequencies, and depending on configuration of inductance and capacitance in the circuit, you have n number of LC oscillators, like we have Armstrong oscillators, we have Hartley oscillators, we have Colpit oscillators, we have Clap oscillators, and there are some more variety of LC oscillators. Okay. Then we have negative resistance oscillators. Okay. A negative resistance oscillator is an oscillator that produces sustained oscillations by using a device exhibiting negative resistance characteristic. Okay. Now, this, instead of relying on positive feedback like feedback oscillator, it utilizes a active or electronic device. Okay. Like for example, tunnel diode oscillators are very popular in negative resistance oscillator. Okay. If you are aware of tunnel diodes, you might be knowing this, but if you are not, okay, and even if you are not aware about a diode, let me reiterate it that diode is a kind of PN junctions, okay, or a simple PN junction can be utilized. If you are not from this background or if you have not studied semiconductor devices, I am talking about a p-type semiconductor and n-type semiconductor. Okay. And when you create this kind of junction, okay, this junction acts as a rectifying junction, okay, and it behaves like a diode. All right. Now, when I am making this PN junction, I am not commenting on any kind of doping profile of this p-type as well as in n-type. Okay. A tunnel diode basically is a heavily doped semiconductor diode which operates based on the principle of quantum mechanical tunneling. Okay, or you can say that this is a quantum device. Okay, and exhibit a negative resistance region in its voltage current characteristic. Okay, they are made from heavily doped p-type and n-type semiconducting materials and have very thin depletion region formed due to heavy doping. And when you have this very thin depletion region, there is always a possibility that electron can tunnel towards the other zone, okay, through these junctions. And because of this tunneling effect only, we call it a tunnel diode. Okay, this is a typical characteristic, a current versus voltage characteristic of a negative resistance oscillator. Okay, you can see that in forward bias, I mean in this biasing condition, okay, when you are increasing the positive voltage, I wanted to mention that this is the symbol of a tunnel diode. Usually I have drawn over here that a diode looks like this and a tunnel diode is represented just by this. All right. So, like if I have this diode, tunnel diode, and if I apply a positive voltage, okay, in forward bias, okay, a tunnel diode conducts immediately due to heavy doping, and you have this tunneling current or you have this current flowing immediately, and the current increases rapidly and reaches a maximum value called the peak current IP at a peak voltage Vp. Okay. When the applied voltage is increased further, the current now in place of increasing starts decreasing. Okay. Ideally, we have seen in Ohm's law also, when you start increasing the voltage, the current is increasing. Okay. Here what is happening is you are still increasing the forward bias voltage, but the current is decreasing. Okay. This decrease continues until the current reaches its minimum value, and this minimum current is known as valley current, IV. Okay. This is your IV at a valley point. Now, this region is the negative resistance region. You see, you are increasing the voltage, but current is falling, and after this valley point, again it starts into normal mode, or it enters into normal mode, which is the conventional diode mode. Okay. The tunnel diodes operate because of majority carriers, and therefore they are very fast. It is possible to make tunnel diode oscillators which operates in the microwave frequency region also. Okay. A simple circuit using this negative resistance device or tunnel diode is shown over here, which can act as a oscillator. Okay. It can be made to oscillate if the correct biasing current is applied to the tunnel diode. Okay. The tunnel diode circuit may use negative feedback for bias stability, just as any feedback oscillator do. Okay. Now, recalling the signal generator, we have just discussed one part of the signal generator, that is oscillator. Okay. The waveform passes through different modulators which shape the waveform into the desired signal type. For example, it can make it square wave or triangular wave, okay, depending on the carrier signal as well as the message signal. Okay. The frequency modulation is achieved by varying the voltage across a variable capacitance diode, or sometimes known as varactor diode, okay, in the tuning circuit of the oscillator. Okay. This gives a system with low output distortion for modulation depth below 1% of the carrier frequency. Okay. Above this modulation level, the waveform applied to the tuning diode need to be deliberately distorted, and this is done in order to compensate for its nonlinear characteristics. Okay. Similarly, the amplitude modulation is also done, and amplitude modulation is most conveniently done by varying the supply voltage to the oscillator itself. Okay. This method is suitable for small modulation depth up to about 50%, and it also gives phase modulation due to the effect of the components used within the oscillator circuit. Okay. Feedbacks can be used to reduce output distortion, and it is known as a envelope feedback. Okay. So, if I say that envelope feedback is a negative feedback technique used in the amplitude modulation system to reduce distortion in the modulated output signal. It ensures that the output modulation envelope follow the input modulation signal accurately. Okay. Envelope feedback is required because in practical amplitude modulation transmitters, amplifier introduce nonlinear distortion which distorts the modulation envelope, and this result in poor signal quality and unwanted harmony. Okay. Therefore, the envelope feedback is used which helps to correct this distortion automatically. Now, let us see that how this envelope feedback works in very brief. Okay. We know that the amplitude modulation output signal is taken from the transmitter output. Okay. Envelope detector extracts the modulation envelope from this output. This detected envelope is compared with the original modulating signal, and the difference, which we can also call a error signal, is obtained. Now, this error signal is amplified and fed back negatively to the modulator, and thus the system automatically correct distortion based on the error signal that is fed. Okay. The output amplifier provides, this output amplifier I am talking about, provides the required signal level and buffers the oscillation from changes in the load impedance. This attenuators is needed to give low level output signals. Okay. For this, usually heterodyne principle is used. Heterodyne principle is kind of idea that you fed multiple frequencies to a nonlinear device, say you fed say F1, F2, maybe more frequencies to a nonlinear device, okay, which can generate output like F1 plus F2, or say F2 plus F2 minus F1 plus F2 minus F1 square, because this is a nonlinear device, it can generate all sort of signals. Okay. So, the heterodyne principle is sometimes used to give a continuously variable wide frequency range output from a single instrument. The signal quality is good, but the frequency stability is poor, especially at low frequencies. And one of the heterodyne oscillator, or one of the idea for the heterodyne oscillator is shown over here. You have oscillator 1 having a frequency F1, oscillator 2 having frequency F2 is fixed to a mixer, okay, and along with a mixer there is a filter also which will filter out any other frequency beyond F2 minus F1. As I have mentioned, you may also have f2 minus f1 square and other higher orders, this filter will ensure that only f2 minus f1 frequency is coming out of this mixer and filter circuit and is fed into this attenuators. Okay. This is because the output is difference frequency, so a slight change in one of the frequencies when they are close to each other can give a wide drift in the output. The output also has a considerable amount of noise and some other disturbing signals. Okay. So similarly, we have multipliers and divider techniques. So multiplier and divider techniques can be used to extend the frequency range available from a single signal generator. Okay. In the multiplier frequency generator, the output from the fixed frequency oscillator is fed through a series of tuned multipliers. As you can see, you have multiplier M1, M2, M3 and so on, each having a non-linear amplifier which produces different harmonics. Okay. The output from each stage is fed to a tuned filter which selects the higher frequency output only. Okay. Frequency modulation may be applied to the master oscillator and amplitude modulation is achieved by varying the DC supply, as I have mentioned, to the last multiplier stage. Okay. The disadvantage of the multiplier generator is that it produces a large amount of noise signal around the desired frequency. Okay. The divider signal generator uses a high frequency master oscillator whose output is divided down by a series of electronic stages, and the output from the divider stage are square waves which need to be filtered to produce a sinusoidal output. Okay. Frequency modulation is applied to the main oscillator if required, and amplitude modulation is obtained by diode modulators in the output amplifier. The divider generators does not produce any noise signal at frequencies below the whatever required frequency is. Okay. Now these signal generators, and we have seen the how to extend its range and all, they can be used for multiple applications, particularly measurement and instrumentations. Okay, like they are very popular in calibrating of any measurement instrumentation. So they can be used to calibrate any standard voltmeter, ammeter, oscilloscope or any frequency meters. Okay. They provide accurate reference signals for all these instruments, and therefore they act as very good reference generators or a calibration generator. Okay. They ensure measurement accuracy and reliability without disturbing any signal from these instruments. Okay. They are also very useful in testing of any electronic circuit, as I have also mentioned earlier. They are used to apply known input signal to circuit of any waveform. Okay, and it helps in performance analysis of all kind of electronic components like amplifiers, filters and transducers, and they also are helpful in detecting fault and non-linear behavior of any amplifier or any other circuit. The signal generator are also useful in the frequency response measurement, and they are used to determine bandwidth and frequency characteristic of different electronic components. Okay. They are essential for filter and amplifier testing and helps in any body plot measurements. Okay. So this is how the signals are generated. Okay. Now once these signals are generated, we also need signal analyzers, or even for other instrument, I mean maybe from transducers directly we may need signal analyzers. Okay. So as planned, let's see what is a signal analyzer in very brief. We will continue our discussion on signal analyzer in our next class also. Okay. A signal analyzer is an instrument used to measure, analyze and visualize electrical signals in terms of their frequencies, amplitude, phase and spectral content. Okay. In any data acquisition system, sensor collect physical signals that we have seen. These physical signals can be of any nature. It can be from temperature, pressure, vibration, whatever, okay, which are converted into electrical signals, and these signals mostly contain noise, distortion, and they may contain multiple frequency components. Okay. Now this signal analyzers helps you to examine these signals, extract only the useful information out of it and understand the behavior of the system, and it also helps you in diagnosing any fault if at all is there. Okay. Therefore, the signal analyzers are essential tools for signal characterization and system diagnostic in modern data acquisition systems. Okay. There are multiple needs of these signal analyzers, as I have mentioned. in practical measurement system, signals are rarely simple. They may contain multiple things, like it may itself contain multiple frequency component, it may contain noises, harmonics, transients and so on. Okay. Now the signal analyzer will help you in identifying all these components and separate out these components, okay, depending on what signal frequency you are using, what bandwidth you are using and so on. Okay. A basic signal analyzer can have, any basic signal can be analyzed in two domain. You can analyze them in time domain as well as you can analyze in the frequency domain. Okay. For time domain, the signal is observed as amplitude versus time. We have seen in previous class that how we can use oscilloscopes to display time domain signals. Okay, like we have seen that in the XT mode particularly, these oscilloscopes can generate a voltage versus time, right? We have also seen that in XY mode it can generate any voltage versus any voltage, say V1 versus V2. Okay. But till now we have not seen that how we can generate X versus frequency. Okay. So in this time domain, like in the XT mode, say I have plotted X versus T, okay, it can be a very good idea to analyze any kind of rise time, peak fall, peak values, okay, a signal waveform and so on using this oscilloscopes. But the real challenge happens when you try to analyze them in the frequency domain. Okay. Now signals can be expressed as frequency components using mathematical tools like simple Fourier transforms. Okay. A signal can be represented in the frequency domain like this. Okay. Now this transformation reveals which frequencies are present in that particular signal. Okay. Now frequency analysis is very important, particularly from a user point of view. For various applications like in the communication system, for the vibration analysis, audio engineering, biomedical signal processing, everywhere you have to have a proper frequency analysis of the signal obtained. Okay. Therefore, the role of signal analyzers become very crucial. Okay. And this goes much beyond than what we have seen in the oscilloscope and other ideas that we have seen previously. Okay. Signal analyzers are classified based on the type of signal analysis they perform. Like we can have spectrum analyzer, we have network analyzer. Network analyzer is again of two types, scalar network analyzer and a vector network analyzer. We have wave analyzers, logic analyzers. Okay. We have vector signal analyzers, VSA, okay, audio signal analyzers, real time signal analyzer, FFT analyzer. Sometimes it is combined with some other kind of analyzer, but we also have separate FFT analyzers and so on. Okay. We also have dynamic signal analyzers, modulation analyzers and so on. Okay. Like if you talk about these analyzers, like say spectrum analyzer, a spectrum analyzer measures the magnitude of the signal as a function of frequency. Okay. So output is a amplitude versus frequency, which you can say that it's a kind of frequency spectrum that is required for analysis of the signal. It is giving you amplitude versus frequency. Okay. And they are very useful in the RF communication analysis, harmonic measurements and for EMI, EMC testing and shielding. Okay. Now similarly we have dynamic signal analyzers, which is used for analyzing dynamic signals such as vibration and acoustics, and it can help you in the FFT analysis, in the transfer function measurement and in the modal analysis. Okay. VSA measures both amplitude and phase and it provides complete characterization of the complex signals. Okay. Their applications is in the digital modulation analysis, wireless communication system and as well as in the advanced radar systems. Okay. Real-time signal analyzers capture signal continuously without missing any transient events, and they can detect even short duration signals and they are useful in the spectrum monitoring. Alright. Now wave analyzers is one of the important signal analyzer and it can measure amplitude of the individual frequency component in any signal. Okay. And they are used mainly for the audio and low frequency signals. They have capability to have frequency selective measurements. Okay. Then we have distortion analyzers, and a distortion analyzer is an instrument which is used to measure the distortion present in a signal, especially in the audio amplifiers, oscillators and in the communication systems. Now there are different kind of distortion that may be available, like we can have harmonic distortion, intermodulation distortion, crossover distortion, frequency distortion, and it can also be distortion in the phase. Okay. Maybe in the next class, we will also discuss the harmonic distortion analyzers in detail. Okay, thank you.